The safety barriers around this junction are coated with a thin layer of zinc. If we look closely at the surface of the zinc, we see it's built up of many different patches. You can find this effect on a number of zinc-coated objects. The patches you see are crystals or grains of zinc. Here's a piece of a different metal. It's been machined along one edge. You can't see any grains in this surface. However, if we turn it over, it's quite a different story. This piece of metal has been broken in half. Along the broken edge, you can see some of the grains from which this material is made. All metals are made up of grains, although you'll rarely see them like this. In fact, with most metals, including this piece of aluminium, the grains aren't visible, not even on the surface. Here's a way of making them visible. First, we must give the aluminium a mirror-like finish. And there we are. Next, we treat the carefully prepared surface with a very powerful acid. Gloves are essential for this operation. As soon as the acid's had time to react, the metal must be washed. It's then given a second treatment with another special chemical. We call this process etching. The particular chemicals used depend on the metal we're trying to etch. One final wash, and there are the grains. Grains of pure aluminium. They're all similar, both in size and in structure. They appear as different shades only because of the way they reflect the light. By etching, we can reveal the grain structure of any metal. Here's a different sample of aluminium. In this case, the grains are much larger and they vary in size. And here's a piece of copper. In this sample, the grains seem to get smaller as you get nearer the middle. Zinc, a sample whose grains are all shapes and sizes. But how do grains form? To find out, we've gone back to the stage when a metal is molten. In this furnace, the metal is aluminium. When the time is right, the furnace is tapped. The molten metal runs out along channels into molds to form huge slabs of aluminium. In turn, the solid slabs will be rolled into sheets. From time to time, a small sample of the molten aluminium is taken for analysis. The metal is poured into a mold and left to solidify. Now we can see what happens as the aluminium solidifies in a special film. At a number of points in the liquid metal, tiny crystals begin to form and grow. Each crystal grows outwards in all directions until it meets the surfaces of its neighboring crystals. In engineering terms, each fully grown crystal is called a grain. In this piece of solid aluminium, there's a very large number of grains. Now, once the aluminium's been cast into slabs, it's rolled into sheets. To get the metal down to this thickness, it's been rolled many times. It's now relatively cold, so as the metal is squashed between the rollers, it's being cold worked. Let's find out what effect the cold working has on the grain structure of the aluminium. Here we're etching a piece of the aluminium before cold working. At this stage, the grains are all approximately the same size and the same shape. Remember, they appear different shades only because of the way they reflect the light. Now we'll cold roll a similar piece of the same aluminium. In one pass, this machine will reduce the thickness by only a very small amount. So we'll reduce the gap between the rollers and put the metal through again. Right, let's see what that's done to the grain structure. The cold rolled piece of metal is the one at the top. Can you see the difference? We seem to have changed the shape of the grains. They've become elongated. We can get a better idea of what's happened in a diagram. First, we'll look at the grain structure of the metal before it's deformed. Here, the grains are normal. But as the metal is squashed between the rollers, you can see how the grains become elongated and distorted in the direction of rolling. The change in grain structure that results from cold working is accompanied by a change in the mechanical properties of the metal. Its hardness and tensile strength increases while the ductility decreases. After cold working a metal, it's usually heated to a sufficiently high temperature. Let's see what effect heating has on the distorted grain structure. In the case of this particular metal, nothing happens until the temperature reaches about 350 degrees centigrade. Now, at the grain boundaries, new grains begin to form. These grow rapidly until a new, undistorted grain structure completely replaces the old, distorted one. We call this process recrystallization. Now let's see what effect this has had on the mechanical properties of the aluminium. Hardness, for example. Here we're measuring the resistance to indentation of a piece of cold-worked aluminium. How does this compare with the size of the dent produced in a piece of recrystallized aluminium? It's much deeper, so recrystallization has restored softness. And what about the tensile strength? First, the cold-worked aluminium. That needed a force of about 7 units to pull it apart. Now for a recrystallized piece. The force is going to be much less this time. The tensile strength has decreased. If we put the broken bits back together again, we find the recrystallized piece stretched the most, so we've also restored the ductility. However, the resulting properties depend on the temperature at which recrystallization is carried out. If the temperature becomes too high, some of the grains will grow at the expense of their neighbors. This can give rise to properties which are highly undesirable for most engineering applications.